Hello. Today we're going to be looking at the average rate of change of functions, what rate of change means and how it relates to maths that we already know very well. The key point to have in mind is that the rate of change in terms of functions or graphs is the same as the slope. So if we're thinking of the rate of change of a quadratic, we're thinking about the slope of a quadratic. What does it mean to have the slope of a quadratic at different points? Or if we're thinking of a straight line, we're thinking about the slope that we're familiar with, that we already know formulas about, that we've been using for years. So slope and rate of change mean the same thing. As an example, velocity, or as we might have called it in junior cycle, speed, is equal to the rate of change of displacement, or as you might have called it in junior cycle, distance. So speed is equal to the rate of change of distance with respect to time. And this is the formula that you would have known for it in junior cycle. S, speed, is equal to distance divided by time. In leaving cert language, we would tend to call speed velocity, so we call it V, and displacement is often called S. So the velocity, or average velocity, is going to be equal to the change in displacement divided by the change in time. So if we were going 10 meters per second, we'd have a change of 10 meters in our displacement for every 1 second change in time. So this is slope and speed and so on that we already know very well. All we're going to do is try and codify what we know and make sure that we're happy that rate of change is a very closely related idea. So if we look at something that we're all very familiar with, my sketch here of our straight line, and if I want to find the slope of my line here between x1, y1 and x2, y2, I'd be looking for the rise over the run, or I'd be looking for y2 minus y1 all over x2 minus x1, or I'd be looking at delta y all over delta x. We know several ways of writing out this type of formula. So let's put that down on paper. We know that the slope of our line here could be written as rise over run. This is a necessary way that we have to be able to think about the slopes of lines, and it's not going anywhere. We know the formula from our log tables, which is another key thing that we need. And we know that we can call that delta y, the change in y, divided by the change in x. And that is, we're now saying, is also equal to the rate of change So the rate of change of y with respect to x would be the long formal way of describing that. All of these are ways of describing the same thing. So the slope is the same as rise over run, is the same as our formula, is the same as delta y all over, or delta x is the same as rate of change. We need this language to be fairly solid for us because it's going to come up in lots of different contexts as we go forward. The next thing I want to talk about is how we can write the normal slope function, y2 minus y1 all over x2 minus x1, in function notation. So by function notation, I mean instead of writing y1 and y2, we are going to write f of a or f of b, where a and b are different values for x. So instead of writing y2 minus y1 all over x2 minus x1, using function notation, my first point, my point 1 would be at x is a, y is f of a. And my second point would be at x is b, y of f of b. So this is my x1, y1, x2, y2. So that would be f of b minus f of a all over b minus a. This function notation will become necessary very shortly when we start to think more about, instead of average rates of change, thinking about instantaneous rates of change. but we'll come to that in due course. The key thing for now is being comfortable that this means exactly the same thing as the formula you are already comfortable and familiar with. Now we're going to put this into practice in this question here. Find the average rate of change of my quadratic here between x is equal to 2 and x is equal to 3. So what do I need? The average rate of change is just going to be using my slope formula. Rate of change means slope. So what would be the slope of my quadratic curve between x is equal to 2 and x is equal to 3? So let's just find that out. So I want, when x is equal to 2, what is y equal to? Well, y is equal to 2 squared minus 2 on 2 plus 2. So x is just going to be equal to 2. And when x is equal to 3, y is equal to 3 squared minus 2 on 3 plus 2, which is equal to 5. So my first point would be at 2, 2. And my second point is at 3, 5. So my slope, or my rate of change, my average rate of change, is just equal to my slope formula. Subbing in, we always write down what we are going to sub in and our formula. And we get 5 minus 2 all over 3 minus 2 is equal to 3 all over 1. So our slope of our average rate of change, the average slope of our quadratic, which obviously doesn't have a continuous slope, it's a curve. Our slope is going to be changing all of the time, but the average slope between 2 points, x is 1 and x is 2 and x is 3, is going to be a slope of 3. Now, this is a little bit abstract, so what we're going to do is switch to GeoGebra so you can see this a little bit more in practice. So this is the result we got by finding the slope, the average slope between x is 2 and x is 3. The screen is about to become a lot brighter. So this is my function, y is equal to x squared minus 2x plus 2, and I have my 2 points A and B put in on my graph, where x is 2 and x is 3. So this is my first point at 2, 2, and my second point at 3, 5. So these are the 2 points I found, and I found the slope in between them. So here I can have my blue line going through here, and I can see that this actually gives me a reasonably good approximation of what the slope of my quadratic is between my points A and B, between x is 2 and x is 3. The blue line is a pretty close fit for my slope between A and B. So this is what we get for an average rate of change. And just to point out to you, we have our line in the form y is equal to mx plus c. So the 3 here is the slope of 3 that we found using our slope equation. Now, moving this a little bit more towards what we're going to be doing in differentiation, how would we get the slope of our quadratic curve not between 2 points, but at 1 point? Say if I wanted to know what the slope of my quadratic curve was at x is equal to 2. Well, perhaps we can see that what we could do is pick 2 points that instead of being 1 unit apart, we could make A and B come closer and closer together. So let's start to move B And when we move B, if we look at the slope, of our line here, it starts off at 3, and as we bring A and B closer together, what would we say that our slope is getting closer and closer to? What value is the slope getting closer and closer to as A and B get closer and closer together? Well, I can see that my slope is getting closer and closer to 2. But I run into a problem when I try to keep doing this, because A and B, my slope that I'm getting here, requires me to have a separate A and separate B. My slope function requires an x1, y1 and x2, y2. So I need 2 points. But if I want to know the slope at a particular point, how would I figure out how to do that? I want to bring my points closer and closer together so that I end up with the slope at a particular point. But I need maths that's going to allow me to bring 2 points closer and closer together without them ever becoming the same point. And to do that, we're going to use the concept of limits that we've touched on before. The screen is going to get darker again. So this is the work that we have at the moment. The rate of change means the slope, and we're already very good at dealing with the idea of slopes of straight lines. We've now touched on the idea of the slopes of non-straight functions like quadratics, or we could have cubics, or we could have circles, or lots of different curves and shapes that would have a slope that was changing all of the time. So the slope is going to change all the way along. As we change x, the slope will change. We now have a little bit of an idea of how it is we're going to find the slopes of our curves for different values of x. So if we combine this idea of an average rate of change with the idea of limits, allowing us to bring the points that we're interested in closer and closer together, we'll be able to get the idea of a rate of change at a point instead of an average rate of change. And we're going to work on that